And thank you all for joining me this morning on this early Saturday morning. I don't know what part of the world you're at, if it's early or late or middle of the day or middle of the morning, but thanks so much for being here. I'm Scott Koziol, an associate professor here at the Baylor Electrical and Computer Engineering Department. So hopefully we have some future budding engineers, electrical, mechanical, aerospace, who knows? So hopefully by the end of this talk, maybe you'll be excited to look into engineering and come into Baylor. You're old enough and ready for that. So, and if you're adults, come on and visit me someday and come see my lab. So first of all, let's talk about robots. So here's a picture of an artist's conception here of a Mars rover. And so what we're going to talk about today is some ideas about robots and why we need to make them really smart so they can think on their own to get some things done. And so you can kind of see this robot here on like a Mars picture there. And actually the US put a robot on Mars just recently. So it was super exciting. So you can kind of see this picture, this artist's conception where it's kind of drilling into the surface of Mars and trying to do some experiments. And so you can think of this as this robot as like its own little scientist. Like this robot is doing some science on Mars. And so more than just robots are concerned, also science like chemistry and things like that. So if you like all kinds of those kind of things, maybe you could partner with a roboticist someday and kind of do some neat science. Okay, so here are some pictures of some robots that some of my students designed a number of years ago. And so there was this competition where they had to, there was a job and they had to like pick up these blocks and they had to design a rover that would collect these little blocks and put them in a little bin on the robot. And so the students used these really cool software to design these robots. And you can kind of see right here, there's a little camera on this one, and the camera went up and it could fold down. And so, yeah, so they designed these. Here's another picture of another entry we students designed, and you can see on this one, it's a robot and it's got a little like, you know how a kangaroo has a kangaroo pouch? Well, this one kind of has a little robot pouch where a little robot was sitting in the big robot. And so the idea was, could this little robot leave the mothership here and kind of do its thing and then kind of go back, and so they could work together. So that was another robot kind of design. We didn't make these, but the students designed these robots that maybe we could have built. Okay, so now you ready to meet some of my robots in my lab? Trying to get some yays, any kids? Okay, all right, yeah, or adults, yeah, all right. All right, so I'm gonna show you this one. So this one is, I'm gonna put my mask back on here so Miss Nancy Garland can help me out. And so I'm going to show you this one. It's made to go outside, and you can do it inside or outside. People can use it for like in dirty environments or agricultural environments. It's kind of rugged. And so the idea is, think of what could you use a cool robot for, especially if you had a little arm connected to it. So think about maybe there's something with farming, maybe there's something with you know, outside picking things up or inside picking things up. And so what I'm going to show you is both these. I don't have my robot arm connected to my robot, but I've got one of each of these things. So let's, so Nancy Garland's going to help me out here. Here is my big robot, and its name is Husky. And it was made by a company in Canada called ClearPath Robotics. And what I'm going to do is I'm going to use this little guy. So does this look familiar to any of you? Any of you play video games? It's a little like controller for video games, like a PlayStation type controller. It's got a joystick and it's got buttons. And so this robot isn't autonomous right now. It's like a big remote control car. And so what I'm going to do is I'm going to control it with this joystick and these buttons. So let's see if we can do this here. Ready? Whoa. All right. So circle. It's almost turn in place. I want to run into something. Cool. Okay, so now I'm gonna get close so you can see it up close. You see this thing right here? This thing right here? Okay, this is called a LiDAR. And what's neat about it is there's laser beams in here that are spinning around in a circle. And what it's doing is it's bouncing off of things. It's bouncing off of me. It's bouncing off the wall. And it's coming back. And using math, we know the speed of light. And we know how much time that laser took to bounce off that wall and come back. And so we can figure out the distance. So by using this little laser thing, it's called a LiDAR, we can figure out the distance to objects in the room. And so with that, we can make this robot say, oh, I know this wall is in front of me. I need to stop, or I need to turn, or I need to go through that door. And so this is a fancy sensor that allows us to do that. And some of your self-driving cars that folks are designing right now, they also use similar devices like this, some of them do, to help them know where they're going and not to run into things. So that's a fun little device. We've also got a camera here. And this little gold one here, can you see that one? This is what's called a stereo camera. And so you see how it has two little eyes here? So think about your eyes. You have two eyes as well, right? So you've got these two eyes, and these eyes help us figure out depth, like how far something is from you. And that's what this sensor does too. It uses the two eyes to figure out some concept of how far things are from them. And it's like, are they in front of something or behind something? So that's another neat sensor. And this guy up here, have you heard of GPS? Have you ever typed into your iPhone and said, where am I? And it tells you, puts a little dot on the screen and says, okay, you're right here. Well, this is kind of a fancy one of those. It's a little more special even than the one in your phone. So, and then I've got a kind of a fancy computer that's inside of this. And it's got little vents here just to kind of blow the heat out. And yeah, so that's, that is my Husky robot, it's called. Okay, there we go. So I want to thank Baylor University for providing me all these great resources and neat robots to put in my lab. And thanks, Nancy, for helping out with that. We might bring you back here just a little bit. Actually, let me show you this one as well. So remember how I said in my presentation there was a robot arm that I could put on top of my robot? So that's what I'm going to show you is this one right here. Okay, do you see this robot right here? So this is a robot arm. And what you do is you program it with how many of you students or parents have an iPad? You raise your hand if you have an iPad? Okay, or used an iPad? Well, this robot gets programmed with something that looks a lot like an iPad. So I can put my hand in here and I click around on it and I can tell this robot where to move. Isn't that pretty cool? It's got a touch screen just like your iPads. And it's, see this little red button here? That's the emergency stop. So if something happens with my robot that I want it to stop automatically, I just hit this special button and it stops. So, all right, I bet some of you parents wish that your kids had an emergency stop button. You can get them to stop what they're doing sometimes when they shouldn't be doing something. But I can do that with my robot. All right, so what I'm going to do is I'm going to start them up and we're going to see what it can do. Okay, so what it's doing is it's picking up this the screwdriver here and it's moving it from one place to another. And it kind of opens its grip and can close down on the screwdriver and move it. So these are kind of robots that you might see in a factory. So you might see these like in a car factory or in making parts for cars. One of my brother-in-law works in a company that has robots, and so that's a good example. Maybe my nieces or nephews online, so hello to all of you. So what's neat about this little gripper, so it's got like fingers, how you can grip things. It's adaptable. So, whoops, it escaped me there. So what I can do is it knows if it's big or if it's small, it can still grip it. So here's the small end, and it still was able to grip it because there's some intelligence in that little gripper that it knows when to stop and when to close, or when to close. Now, I haven't been brave enough to put my finger in there because I don't want it to crush my finger. But now what's also special about this robot is it's made to work in the vicinity of people. So in a factory, some robots you'll see, if you see pictures of robots in factories, they'll have like special cages around them or special walls that separate the human from the robot. And that's because robots can be really dangerous. They're really strong. And if you get near one, it's so strong that it'll push you over and it could hurt you. Well, what's special about this particular robot, it's called my UR5, it has some intelligence in the joints and the computer that controls it, that if I get in front of it and it hits me, it'll stop. Now, it hurts a little bit, but not too much. And I'm going to demonstrate that to you right now. It doesn't actually hurt too much. So let's say I was working along here and I didn't see my robot, and I put my arm here. Oh, see how it stopped? Isn't that neat? So it's a protective stop. It says, oh, I just hit something. I need to stop and be safe. And so that's what it just did. So that's something that's really special about this particular robot. Okay, so we'll maybe save our questions for later. So think about any questions you have about this robot as well, my UR5. So let's meet another robot. How many of you might have a vacuum cleaner robot in your house, like sweeping your floor? So here is a robot by the same, or it's an iRobot. They make Roombas. Maybe you have a Roomba or a Roomba-like robot. So this is like a Roomba. In fact, it used to be a Roomba from the same company. But what they do is they turn them into research robots. I think these might even be refurbished ones, that they go back to the company and then they take out the vacuum cleaner parts and they turn it into a tool that we can use in my research laboratory or in schools and universities and even high schools to do robot tests with. And so it's kind of neat how you can take a robot from one task and repurpose it for other things. So that's my Roomba robot there. Let's see, what else do we have? We've got a couple of flying robots. So here is, it's called an AR drone, and it's a quadcopter. So quad meaning 4. So 4 propellers, 1, 2, 3, 4. And this thing, once these things spin, it can go up and down. Now, you see all this foam here? It's kind of this crushy foam. It's there to protect 2 things. To protect the robot, but it's also to protect you in case it runs into you. So it's good to be safe when you're dealing with all your robots. So that's that guy. And now, see these 2 little special dots on them? They're about the size of maybe a small piece of gum. What's really neat about these, they're reflective. And how many people have seen like an animated movie where they make animated movies like Disney, and they have people and maybe animations in the same movie? Well, what they do, or ways they can make these animated movies, is they have people put on these special suits, and they put these little dots all over the suit, little pearls all over their clothes. And then they use these special cameras to record the movement of the people. And I've got some of these special cameras. I'm not sure if you can see them, but I've got some of these special cameras right here in my lab. I've got 4 of them. This one, that one, and those 2 over there. And so if I put a robot in here with those dots, it'll move around in this space, and these cameras will record exactly where it is. Like super close, like within a millimeter in theory of where this robot is in space. And so what's nice about that is I can know where my robot is, and then I can control it and know where to move it to if I know where it is. So that's a neat thing about these camera systems that I have in my lab. So I've got this little guy, and then I've got another helicopter quad rotor. And this guy is supposed to have this one. One of my students was working on it, so he took the propellers off. So here's the propeller. But in order to be safe, he took the propellers off, so he just put these little pieces of paper so he could spin the motors without having these propellers there that might hurt him. And we didn't want it to take off of the table. So he can just set this on the workbench and spin the motors, but not have it actually lift off the ground and fly into the ceiling. We don't want that to happen when we're just testing it. So you can see it's got a brain here. So this is what we would call the autopilot underneath there. And that is, it can communicate with a radio control. And this is a GPS to tell it where it is. And then it also has, if you look on the bottom of it, it's got a camera. So this camera can transmit what it's seeing down to a person who's maybe on the ground. And then the battery would sit under here in this little pouch. So that is my 3D robotics. And what's neat, maybe you've noticed there's two of these things here. There's actually is built to have a propeller on top and a propeller on the bottom both. And the idea is that it can maybe lift, it's pretty heavy. This guy's really heavy compared to this one. And so having actually 1, 2, 3, 4, 5, 6, 7, 8 propellers, it can lift a lot more heavy things. So that's kind of what's special about this guy. All right, so those are my two flying guys. And then I've got a tiny little robot here. So just to give you a sense of scale, here's my coffee mug. Here's my little tiny robot. Isn't that pretty neat? Like you could actually almost put it in my coffee mug. So this little robot here is called the EPUC robot, and it comes from Switzerland, I believe was where it was made originally. And it's got two little wheels. So it's got this wheel here and this wheel here. And kind of like your Roomba robot, it can spin around in a circle and it can move. It's got a little speaker here so it can make some noise. It's got a tiny little camera right there so it can see things. And then it's got these little black sensors here, and they can sense if it's going to run into something. So that little guy is another little robot, and I have three of these guys. All right.
We have some questions.
Oh, sure. Great.
How long does it take to make a robot like the arm robot that moves the screwdriver around?
Yeah, that's a great question. So I bought this one because it would take a little while to build one of those because you have to build the motors, you have to build the joints and the gearboxes, and then all the computer parts. So what you didn't see is underneath the table, there's a big box right here. It's for all the computer parts. So it would take a little while to build one. And so a lot of my research deals with more the algorithms that run on the computer or run on the robot. And so it'd be cool. And some roboticists do build those kind of robots. But my research is more like, how can I use those robots to do some things instead of building the robot? But yes, you could build one if you want. And you could take some neat classes to figure out how to control all the joints to get the robot to know where to go.
The other question is, what is the most sophisticated robot you have, and what does it do?
Ah, great question. Great question. So both of those are great questions. So I would say this one is my most sophisticated robot. In that it has a lot of sophisticated sensors, and it has the ability for us to program it to do things like, well, actually the sky's the limit. So what I need is you young people to graduate high school, come to Baylor and help me figure out cool things that we could do with it. So yeah, so that's the sky's the limit on what we could do with these things. So great question. One thing it could do is it could map. Like I'm in my research building, and I'm not sure if you can see, there's a big hallway here with other floors. And so let's say we wanted this robot to go out there and like navigate around the building, maybe pick up something and deliver it to somebody. You know, maybe someday if we could merge the arm with the robot, maybe we could have it deliver things or something like that. So lots of ideas.
And what's the current application of the Husky?
Yeah, great idea. I'm actually working with some students now to think about what can we do with it. I grew up in Iowa, so there's a lot of agriculture in Iowa. I know there's a lot of agriculture even in Texas. So if there's anybody watching who has some ideas on how could we use this on a farm or a ranch or something, I'd be interested to know on some good problems on something like that. So yeah, so actually I need folks to help me think of great ways to use the robots. All right, so I'm going to take my mask back off. And let's see how we're doing on time. Okay, 10:55. So I'm going to go back to my presentation here. Okay, so now that you've met my robots, oops, let's see if I can advance the slide here. Okay, and we saw that controller there, that little like PlayStation controller. So now let's think about, can we always use a PlayStation controller? Like, why do we need the robot to think for itself? Like, why do we need to actually program this robot to be smart? If you could use the radio controller to do whatever you want, why would you need to make it smart? So let's think about that. So let's use space and a space robot as our motivation. So we all know space is really, really big, like outer space, right? Like where the planets are. So how many people know how big space really is? Like, do you have an idea of how big space is? Well, let's think about that. So to explain how huge space is, we're going to talk about it in terms of a sports field. And what kind of sport do we all love here at Baylor and in Texas? Football. Okay, so let's talk about space in terms of a football field. So, okay, so here's our players here. Okay, so if this was a football field, this was McLean Stadium, and on right by one of the goalposts, we said, okay, we're going to put that to be the sun. And so there's the sun. We're going to put that right on the left there, that little red dot. There's a more accurate picture of the sun. And let's say we said, let's let the sun be the size of a dime, like really small. And we put it right under by the goalpost there. So let's figure out how far the planets would be if that was our universe. Okay, so Mercury, Venus, Earth, hopefully you remember those from your classes, right? You remember your planets, you learned those in school. All right, so if that was Mercury, Venus, Earth, and Mars, they'd be really close. They'd kind of be in that within the 10-yard line. So they're really close to each other. Still far, but kind of close. Who remembers what planet comes next? It is Jupiter. Okay, so Jupiter would be about there. And then our friend Saturn would be about there. So it's getting pretty far. And then Uranus would be right there. So not even to the 50-yard line, but still far out. And remember, these things are like the size of a dime, approximately. And then Neptune would be out there. And then our friend Pluto, which was a planet when I was your age, and then it wasn't a planet. I think it might be a planet again. I kind of lost track on Pluto. But so we have all these planets. So like think about how if this little tiny size of a pea, that's really far out there. So these are kind of far, but these are really, really far. So that's hopefully helped you get a big of the idea of size of our universe. Okay, so because space is so big, we can't just use our remote control to control rovers. Do you know why that is? Can anybody think of why you can't use like a remote control to control a robot from that far away? Like let's say you wanted to put it onto Mars. Well, if you had Mars there and a little robot on Mars, and you're down on Earth and you have this little communication device to talk to the robot, let's say that was your controller. The problem is space is so far, it takes like 20 minutes for a message to get there and back. 20 minutes. Can you imagine having a conversation with one of your friends and you said, hi, and you had to wait 20 minutes for them to hear it. And then when they say hi back, you'd have to, like this exchange would take forever. Can you try to have a conversation on that? I know we kind of do it with text, and sometimes you can text back and forth in 20 minutes, but if you're trying to get something done, that lag takes forever. And so you couldn't, by the time you maybe turned the robot to avoid a crater, it might have already like gone down into the crater, and no one wants that. So because of that, we need to make robots that can think for themselves, that can protect themselves, defend themselves against, running off a cliff or running into a crater or something. Okay, so that's what we basically said. Because space is so big, we're going to kind of summarize here, and the communication time is so long, we can't really rely on remote control. So we need to make smart robots. So that's our solution. So actually, let's ask, what is a solution? Well, we need smart autonomous robots or rovers. So what does autonomous mean? Okay, so first of all, actually we need 2 volunteers. So hopefully you and a partner at home can do this little exercise in autonomy. All right, so hopefully you have your pieces of paper, and what we're going to do is we're going to make one of you the robot and one of you is going to be mission control. Okay, one of you gets to be the robot and one of you gets to be the programmer. The mission control gets to program the robot. All right, so here's what we're going to do. If you have some space in your room, can you make a pattern? And you don't have to do this exactly. You can just make a boundary. So what we want to do is use your pieces of paper or your note cards and and try to make some sort of boundary for your robot to go around in. And yeah, so if you can do that, you can kind of spread your paper out on the floor there in your room, and kind of just make some sort of enclosed boundary with your squares. And then we want one, and then you can even put one in the middle like I did, so we can have an obstacle that your robot's going to run into. So what we're going to do is we want this robot to get to a goal. So on one of your blank pieces of paper, like put a big old star or something that says, this is my goal. Kind of write that on there. You could maybe put a piece of gold or something. And so what we're going to try to do is in this exercise, the robot person is going to take instructions from mission control. And what they're going to do is they're going to write down some programs. So another piece of paper, we're going to write down some instructions.
Or do you or is it someone else?
Those instructions are going to be directions, like steps. So did you ever play the game Mother May I? And I think that game was like, you know, can you take a step forward? And you'd say, Mother May I? Anyway, this game is you're going to tell the robot to take a step forward, or to take a step to the right, or to take a step to the left, or to take a step backwards. So those are your 4 commands. You can go forward, backwards, left, or right. And each command is like 1 step. So we're going to put a series of steps together to get the robot from its home to its goal. And this is like a program. So we're writing a program. So how many of you have written a program before? I can't see everybody. So, oh, I see a hand raised there. Okay, great, great. So what we're going to do is we're going to write a program, and it's really simple. Our program consists of, and you can actually do this. We're going to use arrows to make it even simpler. Okay, so mission control is going to create a list of robot moves, one of 4 moves, to collect the stars, and then the robot will perform the moves. Okay, so here's an example with my little boundaries. The first step is going to be forward. Another step is forward. Another step is forward. Another step is forward. And then you're there. So those little 4 steps gets to the goal. Now let's say I want to go to the other star. Well, I need to take a left turn, and then I need to go straight, and then take a right turn, then go straight, and then take a left turn, and then take a right turn, and I'm there. So those are the actions. See how I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Those are my steps. And so I'm going to put those steps together into a list of commands. So those are my commands, like right, 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 and then kind of collect those arrows. So if you can write, that's all you need to do is just write like to the right, and collect those arrows into a list. And then what we're going to do is once you have that together, mission control is going to read off the list. They're going to say 1 forward, 1 right, 1 forward. And the robot can perform the moves and collect the stars. But here's the trick, or here's the complexity. The robot is going to have to cover its eyes. And so the mission control needs to have a really good command here. So the robot's going to cover its eyes, and the robot's going to take a step. And what we're going to do is we're going to see if the robot can actually get to the goal based on your steps. And it's going to be kind of hard. So let's try that. So, okay. Does everybody have their boundaries made? I'm going to see if I can see all of you in my grid view here. Right, so I can see some, okay, I see some white pieces of paper out there. Great, great. All right. Okay, so So what you need to do is make your list of arrows, and we'll take a few minutes to do that. And if you make it smaller, it might be just less time, but okay. Does anybody have any questions about what they're doing? Oh, I see some folks are doing the stepping. Okay, you got to close your eyes too. That's part of the trick. Or not trick, it's part of the challenge. Because if a robot can't see, so if a robot didn't have any sensors, and you just gave it a list, it's kind of actually hard to do. All right. So I see some of you. Okay, yeah, I see some folks are getting ready to do it here. All right. Oh, there's someone. Okay. Oh, you're on the table. Okay. A brave soul there. All right. Okay, I see some more folks are getting ready to do it. And it's okay if you run into one of the sheets, because actually we're learning that it's actually pretty hard to give a list of commands to a robot and have it do what it needs to do if it can't see. Okay, is anybody finding out that they're running into some of the boundaries? So hopefully you learn some things about how hard it can be to actually try to figure out how to program a robot. Can be kind of hard, right? Like if the robot, all it does is do the commands that you give to it instead of having some intelligence, it can be really hard, right? So if you put a list together, maybe the person who put the list together didn't realize that there was a white square in the middle of everything else, and you'd run into it if you didn't have like some sensor, some eyes, or some sort of way that the robot could say, oh, whoa, there's a white square here, I can't run over that. So this is another reason that we need to make robots, give them some sensors and to kind of help to think for themselves, some sort of processing to think for themselves. Okay, so I'm gonna move my screen here. Okay, so when we talk about a robot and helping it think for itself, we call that autonomy. And let's see, I am going to move my screen. Okay, so the fancy word for teaching a robot to think for itself is autonomy. Okay, so autonomy is this fancy word that says how much can the robot think for itself? And so we've got kind of different levels of autonomy that the robots have. And so I'm going to have couch these in terms of like your growth. So when you're a baby, you didn't do much for yourself at all, right? Your parents fed you and they gave you clothes and they kept you safe because you were kind of just there in the little crib, right? And that's kind of like a robot that we have to do everything for it. Like it doesn't have a lot that it can do on its own, but babies grow and we can make robots that have more advanced capabilities. And so eventually a baby starts to feed itself, right? It can use the spoon, it can do things on its own. And so we can make some robots that can start to do some things that for itself, if you will. And then there's a kindergartner. At this point, you're doing things for yourself, right? You're picking out what clothes you want to wear and what food you want to eat. And then when you're middle school, maybe you make decisions that are shared. Like you can talk with your parent about decisions. Like, do I want to take music? Do I want to do sports? Do I want to take art? And so it's like what we call shared control. And so maybe the robot and the operator both have like some decision making. And then when you're high school, it's kind of also blended decision making, but maybe you ask, hey, can I go to this party and see my friends? and then the parent would give approval and say, yes, you can. Is it a safe party to go to? Is your homework finished? And so maybe the robot, based on its sensors, says, okay, I think I can do this move, but I want to ask mission control just to confirm that that's a good move to make. Or whatever your application be. Maybe it's a flying robot and it makes a decision. And then when you're in college, there's supervisory control, we'll say. So maybe you select where you want to go to college, hopefully Baylor, and your parents check you in, drop you off, and maybe send money as needed or when you call home. And then finally, when you graduate or when you're an adult, full automation, you're responsible for your actions. And I guess we're always responsible to someone, and so you have a lot more autonomy. So those are kind of different levels of autonomy, just kind of in our growing up process. And I like to draw this arrow because it's basically increasing autonomy as we get older, and the same for robots. We can design a robot that can't really think for itself, like fully remote control, all the way to the goal would be, can I design a fully autonomous robot that can do a lot of thinking by itself? Okay, just a few more slides here. I know we're getting close to the end. So think about how a robot moves. The fancy word for that is called locomotion. So locomotion is the fancy word for moving. And there's lots of kind of motion. So what kind of motion did we see with my robots here? We saw flying, and we saw wheels, but there's actually more types of locomotion. So we can walk. There's a company called Boston Dynamics, and they make walking robots. And it can actually do fancy things like backflips and stuff too, if you can see some videos on that on YouTube. So walking robots, there's a picture of my rolling robot, my flying robot, or flying robots like mine. So what about this? It's a snake robot. See how it has these little joints here? It can actually slither. So maybe if you have a pipe that you want to inspect, you could put this little robot inside of the pipe, and maybe it could slither through there and look for maybe debris in the pipe or something that's stopping up the things from moving inside the pipe. So a snake robot. How many people have thought about a snake robot before? It's pretty cool, huh? And then the last one here, a swimming robot. How neat is that? So here's a little swimming robot in a pool, and it kind of looks like a person. So it's got little jets here and some sensors, probably some eyes and some hands. So swimming robots too. Okay, so study hard in school if you want to do robots. Study hard in high school, study hard in college. Here's just an example of a place that you might want to work someday. If you like space robotics, this is a Jet Propulsion Lab at Caltech's in Pasadena, California, and they do some amazing things with space robots, like they put rovers on Mars. So come to Baylor and keep studying hard in school. So with that, thanks so much for listening and for hearing about my robots. Yeah, I'm going to put my mask back on, and we're going to take some questions.
Would a student that's interested in robotics apply to computer engineering or mechanical engineering?
Yeah, that is a great question. So you could actually do both. So when I was in school studying about robotics, some of my friends in school were studying in mechanical engineering, and some were in electrical, some were in computer science, some were even in aerospace engineering. So there's a lot of disciplines that can get involved in robotics. So really, it's kind of about your passion. If you like to, if you like more mechanical things and figuring out the angles and things like that, maybe mechanical is your bent. If you like flying things, maybe aerospace is the way you want to approach it. If you like the computer programming part, maybe you want to be electrical or computer science. So really, there's a lot of opportunity.
Also, how does robotics tie into artificial intelligence?
Yeah, great question. So there's a lot of people who, it's okay, it ties in really well. So artificial intelligence, we need for a robot to think like this guy. You might have heard of things called neural networks or deep learning, and those are kind of popular artificial intelligence methods. And so that, like, in my lab, we're actually looking at trying to get a fancy little computer thing that we're making to recognize images in a special way. And so artificial intelligence we're using to say, you know, is this, what am I looking at? Am I looking at this thing or am I looking at something else? And so robots can use artificial intelligence to do things like that. So pattern recognition, it's called. That's the fancy word.
And where some of your students have gone on to what type of jobs with robotics?
Oh yeah, great question. So I'm trying to think if anybody's doing work in robotics. So I actually, my research spans kind of a lot of different things. So I try to combine neuroscience with robotics with special electronics. And the fancy word that is combining neuroscience and electronics is called neuromorphic. So neuromorphic. And the idea is, and I'll answer your question about where they've gone to work. The idea is, can we make smarter brains for robots that are inspired by our brains? So somewhat, as far as like where my students got jobs, one went to Lockheed Martin, one went to kind of more of an aeronautics company, one went to Samsung Electronics, General Motors. Yeah, so those are some of them. Yes.
And where did you go to college?
Okay, so I went to undergraduate school at Cedarville University in Cedarville, Ohio. And then I went to Iowa State University for a master's degree in electrical engineering. And then I went to Georgia Institute of Technology in Atlanta, I did a master's in mechanical engineering and a PhD in robotics at Georgetown.
What are some of the biggest challenges for designers at this point?
Yeah, great question. So artificial intelligence is a really hard field. So someone mentioned AI or artificial intelligence. It's a complex thing to do because the world is really complex. Like we kind of take for granted how easy it is for us as humans. I think God designed a really amazing system of our brains, but we can see things and make decisions. When you see a tree or a bush, you know it's a tree or a bush. But a robot you have to teach it. Is that a tree? Is that a bush? Is that a plastic bag that's like rolling across the road? Like when we drive and I see a piece of cardboard kind of floating by on the freeway, I think, oh, it's a piece of cardboard. It's a plastic bag. If I hit it, it's not going to be like the end of the world. But if the robot doesn't know, if the robot thinks that's a solid piece of metal, it might have to veer off or something. So I think teaching an autonomous system how to interpret its sensors is a really hard task to do really well all the time.
I wish I had a robotic hand to keep this camera still. So I thank you all for allowing me to make mistakes here.
Oh, you're doing great.
Are there any other questions? What I wanted to let you know is that please contact me or Scott, and we are filming this. If you want to share or see this again, share it with other friends or your teachers. Please feel free to. We'd also like some comments from you. And I think Celeste, will you be sending out an email with comments and questions?
Yes, you should be receiving a follow-up email sometime next week from Baylor alumni, and there will be a link to a survey. If you could complete that survey for us, we would really appreciate it. There'll also be a link to the recording of our session today. So thank you, Dr. Koziol.
Great. Thank you, Celeste, and thank you, Nancy, and thank you all of you for attending. It's been really great to meet you all, and thanks so much for sharing your Saturday morning with me.